Ionic radius is referring to the size of an ion. In a previous video, I talked with you about atomic radius. Remember, this is just a fancy way of referring to the size of an atom. And in that video, I told you that atoms get larger as we go down any column on the periodic table, and this is due to increasing the number of energy levels in an atom. Also, atoms get larger as we go from right to left across any given row, which we talked about how that seems kind of counterintuitive, but as we go in the opposite direction, as we go from left to right, effective nuclear charge increases, which has the effect of pulling the electrons tighter and tighter into the nucleus, which results in a smaller size. So the atoms on the left side of any given row are always going to be larger than the atoms on any right side of a given row due to their difference in effective nuclear charge. Now, in this video, we're going to be talking about ionic radius. And ionic radius is a little bit more difficult to draw a trend for in the way that we've done with atomic size. First of all, let's just cover the easy part first. Ions, just like atoms, ions get larger as you go down a column. So from top to bottom on the periodic table. And the explanation for this is the same as the explanation that we use for increasing atomic size. So this is just simply due to increasing number of energy levels, which we abbreviate as N. The atom or the ion just gets larger and larger and larger as the number of energy levels are increasing. So this is, like I said, this is the easy part of the trend. Now, if we're looking at within a given row on the periodic table, the trend actually depends on if we're looking at a cation or an anion. So we're going to make two explanations here for cations, first of all, and then also for anions. So in order for us to understand why cations and anions take the size that they do, we have to think a little bit about what's happening when an atom becomes a cation and what's happening when it becomes an anion. Remember, with a cation, this is where we have a number of protons greater than the number of electrons. So a cation is the result of an atom losing one or more of its electrons, and therefore the protons are outnumbering the electrons. So if we're thinking about this from the perspective of the atom, we've got this positively charged nucleus in the middle, and it is surrounded by our electrons in the electron cloud. And remember, these electrons are feeling effective nuclear charge of this nucleus. If the nucleus magnitude of its positive charge is greater than the magnitude of the negative charge from all of those electrons, because the protons are outnumbering the electrons, so the nucleus is more positive than the negativity of the electron cloud, this increases effective nuclear charge and results in all of the electrons being sucked tighter into the nucleus, ultimately causing the cation to have a smaller size than its corresponding atom. Cations are smaller than their corresponding atom. I'll explain what I mean by corresponding atom in just a second. Cations are smaller than their corresponding atom, and this is because losing one or more electrons causes an increase to the effective nuclear charge. And as we've seen from previous videos, increasing effective nuclear charge just simply means that this causes the atom to shrink, or the ion, I'm sorry, shrink. So what do I mean when I say the cation is smaller than its corresponding atom? That just simply means, for example, the sodium cation, I don't want to write it up there, the sodium cation is smaller than the sodium atom. So we can only make a comparison between the ion and its comparable or corresponding atom. But this is going to be true for any cation. So a calcium cation is smaller in size than a calcium atom. And that's the trend, which we really can't represent with any kind of arrows. All we can say is that a cation is always going to be smaller than its atom. Now, for an anion is an atom that has gained electrons. So in an anion, we have the number of protons less than the number of electrons. So you might be able to anticipate that we're going to have basically the opposite effect here. We've got our nucleus, we've got our electron cloud out around it, and this time the electrons are outnumbering the protons in the nucleus. So the electrons have a decreased sensation of the positivity of the nucleus. Their effective nuclear charge has gone down, which causes them to kind of expand or move away from the nucleus. This causes anions to be larger. So anions are larger than their corresponding atom. And this is because gaining electrons decreases the effective nuclear charge, which expands or increases the size of the ion compared to the atom. And again, when we're looking at the size of anions, we can only compare an anion to its corresponding atom. So we can say that the fluorine ion is going to be fluoride ion is larger than the fluorine atom, or the chloride ion is larger than the chlorine atom. But what we can't do is, for example, compare the size of fluoride with chlorine, or fluoride with calcium. We could kind of do that kind of thing indirectly, but definitely we can't make a quick and fast comparison between an ion of one atom and an atom that's completely different.